Dr. G. Shukuma to all the participants of this FDP. Madam.
Thank you, sir. It gives me an immense pleasure to introduce today's presenter, Dr. G. Shivkumar. Dr. G. Shivkumar graduated from MCE Hassan in Instrumentation Technology, obtained MTech degree from Indian Institute of Technology, Kharagpur, with specialization in instrumentation. Completed PhD from VTU Belagavi in the area of pattern recognition and affective computing. Postgraduate diploma in HRM from KSOU, Mysore. Started his career as a lecturer at MCE Hassan in the year 1990. Sir has published over 60 research papers in the peer-reviewed journals and over 40 papers in the proceedings of conferences of repute. Through UGC international travel grants, he has visited Singapore, Malaysia twice to present research findings at the international conferences. Authored a chapter in the book Synthesizing Human Emotion in Intelligent Systems and Robotics. He has organized 22 FTPs for Faculty of Technical Institution in the area of embedded systems, instrumentation, and quality initiatives in engineering education. He has delivered invited talks in the domain of embedded systems, ANN, affective computing, and engineering education. Currently, 6 research scholars are pursuing their PhD program under his guidance. He is investigator of many funded projects from AIST and DST. Sir is serving as a member of BOE, BOS, and doctoral committee for various universities and institutes. In the past, he has worked as Dean Humanities and Institute level MBA coordinator of Malnad College of Engineering. At present, he is working as Dean R&D professor and head at the Department of E&I Engineering. Also as the coordinator of the Internal Quality Assurance Cell. So I welcome you once again, sir, on behalf of our college. Sir will deliver a talk on affective computing, pertinence of biomedical engineering. Sir, you can take over, sir.
Yeah, thank you, Dr. Poli, my good friend, and Pushpalata madam. At the outset, I extend my sincere thanks to UBDTCE, in particular, Dr. Mallikarjun S. Poli, my good friend, for giving me this wonderful opportunity to spend this morning sharing my thoughts with the august gathering, faculty members across the country from the nook and corner of India. So I feel myself fortunate. For today's presentation is topic of today's presentation is affective computing, pertinence of biomedical engineering. In fact, biomedical engineering application to the area of affective computing. In a duration of 1.5 hours, I will speak about affective computing and how a machine learning can be used in computing. And I will share you and explain you the script which is written in Python for affective computing. Exactly, this is, we are in the middle of this FDP. 2 days and 1 session is over. And 2 days and 1 more session after my session is left. I am exactly at the middle. Maybe some of the topics that I am going to discuss will be a repetition, since already many sessions are over on this biomedical engineering and machine learning. So kindly bear with me if there is any repetition. Just a second.
Excuse me, sir.
Since due to the problem of bandwidth, I am putting off my camera. Okay.
Okay.
So,
we cannot see your screen, sir.
Is my slide
Sir, slides
is my slide visible now?
Yeah. Now it is visible.
Just is my slide visible?
Yes, sir. Yes, sir. It's visible. Sir, audio is breaking, sir.
Okay. I will come closer to my microphone. Is it audible now?
Yes, sir. It's audible, sir. The slides are visible, sir.
Are you able to hear?
Yes, sir. Yes, sir.
Okay. Okay.
Thank you, sir.
Affective computing is an area of research which is gaining prominence day by day. So the term affective computing has nothing to do with effective computing, where it is efficient computing. Affective computing is more related to emotion. The term was coined at MIT, Massachusetts. For the first time, MIT, Massachusetts has developed an affective computing laboratory. The pioneer in this field is Dr. Rosalind Picard, who is a lead scientist at MIT, Massachusetts. They have developed an affective computing instrument. I will play a short video at the end of this session about the developed instrument which is used in affective computing. So this is the agenda of my presentation. Introduction, what is affective computing, Anderson's affect wheel, what are the different modalities of detection, the facial expression and its recognition, what are the physiological parameters which are useful in affective computing, what are the paramount features which are needed, then a classifier using artificial neural network. Since this is a totally new area, we don't have any database in this field, and we have created our own database. I will discuss about that one. EMCE database, Malnad College of Engineering database. Conclusion, future scope, a mood meter, and selected references. This is my agenda for today's presentation. Let me start with a thought process by Arnold Bennett, a British novelist and playwright of 1867 and 1931. There can be no knowledge without emotion. We may be aware of a truth, yet until we have felt its force, it is not ours. To the cognition of the brain must be added the experience of the soul. This is what is an affective computing. So, affective computing is an area which deals with emotion. Nowadays, in the corporate world, emotion intelligence is a buzzword. A person with good IQ and EQ will be productive to a company. He can contribute to the growth of a company, he or she. That's what corporate world today thinks. While recruiting, while hiring, the corporate world not only looks at the intelligence quotient of a person, it also looks at the emotional quotient. If both intelligence quotient goes hand in hand, they know a person is balanced. Right? So emotion is a distinctive type of mental state with bodily changes, expressions, and actions. Emotion is an excited mental state, we can call. It is an excited mental state. When the mental state is excited, it will be exhibited by a person by means of bodily changes, by means of expressions on the face, by means of actions like then most of the expressions are involuntary in nature. If it is reaction, then it must be involuntary in nature. And the use of biomedical or physiological parameters, to be precise, is to avoid any of the voluntary expressions which we call as imposed. To avoid that one, we have to go for physiological parameters in addition to the physical bodily changes of a person. During immediate reflex, it's almost impossible to curtail our expression. So whenever we want to express an emotion involuntarily, spontaneously, as an immediate reflex to a situation, then it is almost impossible to curtail. The two physiological parameters are not at all possible to curtail. So I want to show this in an image. Signs of low emotional intelligence. We have seen many people in our day-to-day life with very high IQ but very low EQ. And how they exhibit it? They are normally argumentative. They don't listen. They always tries to speak without listening. They always blame others. And there is an emotional outburst. They respond immediately, spontaneously, without having a double thought about that one, thinking twice on that one. So these are some of the signs of low emotional intelligence. But at least we have to control this emotional intelligence. So as you know, to control anything, we need to measure it. And whatever I discuss today in the coming slides is all on measuring these emotion. Coming to the affective computing. Affective computing is the study and development of systems and devices that can recognize, interpret, process, and simulate human emotions. The field of study in relation to human emotions is called affective computing. We can recognize, interpret, process by using different modalities. It need not be only physical, it could be physiological, and it could be a fusion at the sensor level and at different levels. It is an interdisciplinary field, affective computing, spanning computer science, psychology, cognitive science, biomedical engineering. So it is basically affective computing is the application of computer science into the neuropsychology. Human emotions are different types. There are different types of human emotions. But neuropsychologists, researchers have identified these 6 as basic emotions. There may be few more type of emotions, but they are not considered as basic emotions. First one, surprise, fear, disgust, anger, happy, and sad. Okay, so these are the 6 basic emotions. So each one is represented by emoji. It is classified first by an American researcher called Paul Ekman, who scientifically proved that there are only 6 basic emotions. And what are the emotions we have, the remaining emotions? They are all secondary emotions, which are the result of many basic emotions. Right? So you can see here, these are facial expressions. You can see the shape of the eye, then the color of the eye, eyebrows, opening of the mouth, stretch of the nose. These are all the facial expression features for identifying the emotion. And one of the major problems or the drawbacks with facial expression is I can act, even though I'm not sad. I can act like I'm sad. Even though I'm not happy, I can show a happy face to everybody. That is why only facial expression, even though 60% of the time human emotions are expressed through the face, the facial expression is not considered as a robust method of detection of emotion because of this imposter. Hence, we have to resort for other methods where this type of enacting is not possible. Biomedical engineering is one such. There are some secondary emotions which are not there in those 6 basic emotions like pain, love, contempt, cunning, the list goes on. So these are all treated as secondary emotions. In my presentation today, I am focusing only on basic emotions, those 6 basic emotions. Affective computing is always confused with sentiment analysis. There is a slight difference between sentiment analysis and affective computing. Though these are the two areas closely related to neuropsychology, a sentiment analysis measures the subjective polarity. Example of this one is crowd behavior analysis. In case of crowd behavior analysis, we are not specific about what an individual is doing and what is the exact emotion of an individual or a group. Instead, we look at the polarity in the sense, is the crowd going violent or is the crowd behaving in a peaceful way? So we look at only whether it is going towards a positive way or negative way to take further action in terms of law and order. Whereas in case of affective computing, it concerns with the identification of explicit emotional status. If a subject is given, then my job here is to identify whether the expression of that person indicates a happy, sad, anger, disgust, etc. Identifying an individual emotion which could be either primary or secondary. So this is one of the important way of representation of emotion. It's called as Anderson's affect wheel. Anderson, a neuropsychologist, who devised this wheel, which indicates a different status under different conditions. Here, there are 2 inputs. First one is called arousal, and second one is called valence. Valence is represented on the x-axis, and arousal is represented on the y-axis. And arousal is a physiological or psychological state being awake or reactive to stimuli and readiness of a person to respond. That is called arousal. Arousal is a readiness of a person to respond for a stimuli. Then what is a valence? It is the goodness or badness of an event or situation. Valence represents a situation, whereas arousal represents the response of a person to a specific stimuli. And you can see here, the best one is here on this quadrant. So if the valence is positive and the arousal is negative, it is pleased, satisfied, calm. This is content. And the worst one is if the arousal is also negative and the valence is also negative, it is in miserable, bored, tired, totally it will be in depressed state. And in the remaining 2 quadrants, we can see if the valence is say negative and the arousal is positive, it is an angry state, alarmed, annoyed, frustrated, etc. And on the positive side, if the valence is positive and the arousal is also positive and it is joyful, it's delighted, glad, etc. Okay, so this Anderson's wheel gives us the different emotional status if arousal and valence is taken into account. Then coming to the detection modalities. What are the different modalities by which we can detect emotion? First one, the basic classification. It is in unimodal or multimodal. In case of unimodal, it is the facial expression. Either we can use an optical image, a light image, or we can use an IR image, a thermal image for analysis. Second one is speech, the vocal utterances. So to stimuli, a person responds. So happy will be responded in speech in a different way, angry in a different way. And if we do speech analysis, we can detect it. Gesture. Gesture could be a bodily gesture, hand gesture, etc. The first three, they are basically considered as the physical parameters. Then from 4 to 9 are the physiological parameters, which are closely related to biomedical engineering. First one is electrodermal analysis, EDA. It is also called as galvanic skin response. So one of the important parameters which gives information about the emotional state of a person. Second one is the temperature. Body temperature normally measured at the fingertip. Next is the heart rate. Then ECG, electrocardiogram, electrical activity of the heart, EEG, electroencephalogram, electrical activity of the brain, EMG, electromyogram, electrical activity of muscles. Then 10th one, which is beyond the scope of our discussion today, written information. So depending upon the emotional status, the information written by a person, the words used by a person also changes. It is an indication of the emotional state of a person looking at what the person has written. These are all unimodal detection modalities. Next is the multimodal. Here using more than one mode. There are three different types. One is the fusion at the sensor level. Second one is the fusion at the feature vector level. And third one is the fusion at the classifier level. So in the case of sensor level fusion, we can use more than one unimodal detectors. In the sense, use facial expression along with vocal utterances, use facial expression along with EDA. It is the fusion at the sensor level. And if it is the fusion at the feature vector level, for example, I consider only face. In face, we have different feature vectors. In the sense, what is the opening of the mouth? What is the total area of white pixels in the eye? So first feature is the opening of the mouth. Second feature is the total white pixels in the eye. Next, eyebrow constriction, length of eyebrow constriction. These are the three features of the same facial expression. This is called fusion at the feature vector level. And last one is the fusion at the classifier level. Here we can use more than one type of classifier. I can use a simple ANN, or I can use an SVM. I can use a genetic algorithm and get the result of all the three, and get your classifier will be the best out of the three. The best score out of the three can be treated as the output of the classifier. Right? So these are the different detection modalities in affective computing. I have shown here some of the applications of affective computing. It can be used in management and marketing, like strategy development, brand management, churn prediction, preference learning, preference of the people. Each time by talking to the people, we can do the market analysis. We can, strategize what we have to do next in case of marketing, in case of a product development. In the same way, in finance, investment decision, economic growth indication, then in education, e-learning. So probably in the days to come, so e-learning will be the order of the day, where by using these affective computing tools, we can identify whether our student is interested in our lecture or not. So what is the response to the instantaneous response to my student to my lecture? So that how can I overcome? If the student is in a bored state, then how I can take him out of that state? So all these comes in this application of effective computing. And in the healthcare, depression treatment, suicide prevention, public health forecast, diagnosis, and in politics, political participation of the general public, then public monitoring, in which way the trend is going. All these can be done. Then finally, user interaction in social media. We have today social media is very active, and what is the sentiment of the public, what are the emotion expected, which can be used in by the government and law enforcing agencies at different levels. This one, somewhere I have downloaded this one, a survey conducted by an institute. If an instructor uses humor in the class, what is your response? A majority of 81% students responded, we will learn more. 1% response, we will learn less, and 32% response, it makes no difference for us. So it clearly indicates if we very interactive in the class, if we monitor the emotion of those who are listening to us, definitely it will reach them in a better way. I thought I can put this cartoon. It is an EQ test in a company. I just read it. I am sorry to say, but you have failed in your test because you did not even make a sad face when a sad story was being narrated to you. Okay, so whenever a sad story is narrated, at least make your face as a sad face. We must have an instantaneous reaction to a situation. That is what an emotional is. Now I will first discuss about the facial analysis module. Then I will go to the physiological signal. First is, in case of facial analysis, we need to detect the facial expression. Prior to the facial expression detection, if we are given with an image of, say, image of the body, where face is to be identified first, detection. That means localization of the face. Finding a face without prior information about its location. Face has its own distinct feature. 2 eyes, 1 nose, 2 eyebrows, 1 mouth, 2 cheeks, etc. This is a distinctive feature of the face. By using different image processing technique, we can easily localize a face in a group or in the entire body. So using prior knowledge about where to look, we can track the face. Already even in mobile phones, in smartphones, we have this feature. A face is recognized, a face is tracked. And in the next stage here in the emotion recognition, extraction of key regions and points in the face are very, very important. What are those key regions and what are the points of interest that I will discuss in the coming slides. Next is the biomedical signals, which are of importance in emotion recognition. Already I have listed in one of my previous slides. Again, I am showing it. EEG, respiration rate, blood volume pulse, then GSR. Even the blood volume pulse is used for measuring heart rate, photoplethysmograph. Then GSR, and acoustic and noise, that also considered as a part of biomedical signal, temperature, EMG, EEG. In case of biosignal analysis, different emotional expression produce different changes in the autonomic activity of the body. So anger, fear, happiness increases certain parameters of, say, heart rate, skin conductance, temperature, etc. I will discuss in detail about this one by taking the individual parameter, say galvanic skin response. What galvanic skin response decides and what are the parameters that it will vary, whether it increases or decreases, etc. So in our lab, 4 of my students are working in this field for a PhD program. This is a general signal acquisition environment. We use LabVIEW for signal acquisition. For the later stage analysis, we are using Python programming. You see here, a subject. So we call a person whose emotion is to be detected as a subject. First, emotion is excited by showing a video clip or an audio clip to the person, which will elicit emotion in that person. Prior to that one, there is a survey form. That survey form is to be filled by the subject. So what is the age? What is the social background? Okay, so there are some people, even a horror movie is shown to them, they don't fear. So because of their background, social background, their psychological behavior, etc. Looking at all those things, the parameters like facial expression is captured using the camera. Then it is the video sequence. That video sequence will be converted into image. Then image will be processed, or video sequence itself will be processed. Then for physiological parameters, sensors are used. For galvanic skin response, for fingertip temperature, and photoplethysmography, sensors are used and they are connected at different locations, and the signal is acquired. These are the physiological signals using LabVIEW. So this is a general block diagram of signal acquisition. There are some observed cues for facial expression. For surprise, so eyebrows are raised, curved and high, skin below brow stretched, eyelids opened, jaws drops open without tension or stretching of the mouth, etc. The image that I have shown below is the subject, my research student Naveen Kumar. In the same way, for disgust, so there are a list of facial expression cues. Upper lip is raised, lower lip is raised and pushed up to upper lip, nose is wrinkled, brows are lowered, lowering of upper lid, right? So in the same way for fear. Okay. So in this case, it is not the output of the actual signal acquisition. That subject was told to enact like that, enact as if you are fear, enact as if you are very angry. In the same way for anger, for happy, yes, here he is really looking happy. So for happy, so these are the features of the facial expression. And for sad, there are a list of facial expressions. I will not read each and every line. So it is simply by looking at the image, we can decide what the emotional status is. So in the nutshell, in a facial expression recognition, the regions of interest are the one in the background here is the facial image. It is a thermal image. Thermal image converted into a grayscale image. Thermal image, if we capture through the thermal camera, through an IR camera, it will give us the temperature distribution on the face. It is captured by using IR camera. Then we have converted it into grayscale. And the regions of interest in the face, it is same for both thermal image as well as a normal photo image. The first one is the forehead. It is the forehead region. The wrinkles on the forehead is an indication of different emotions. Second is the eyes region. In the eyes region, we have left eye, right eye, eyebrows, etc. Then the cheek region, both left cheek and right cheek. Especially in thermal imaging, the area where the temperature is more is the cheeks. Then the nose. At different emotional status, nose will be stretched. The length of the stretch, the vertical length of the stretch will indicate what the emotion is. Then mouth. So normally the mouth region, the whole mouth is normally treated as an ellipse. the major axis and minor axis of the ellipse at different emotional status will give us the information about the class. Next is galvanic skin response. The features, the biomedical features that I have considered in my work is three. First one is the galvanic skin response, which is nothing but electrodermal activity. It is the response on the skin. Second one is fingertip temperature, and the third one is heart rate. In addition to that one, 5 facial parameters are considered. 5 plus 5 facial parameters plus 3 biomedical or physiological parameters. First, what is a galvanic skin response? The galvanic skin response is one of the several electrodermal responses, EDRs. EDRs are changes in the electrical properties of a person's skin caused by an interaction between environmental events and the individual's psychological state. The following changes in GSR are expected in different emotional states. Okay, so GSR is the galvanic skin response, a small change in the resistance on the skin, which is normally measured between the index finger and the ring finger. We have a GSR meter. GSR meter is connected in between the index finger and the ring finger. And the small change in the resistance or the conductance, in fact, is converted into a waveform that I will show you in the program that I will execute now, the Python program. And what are the different emotional status that can be detected by simply measuring? You can see here, all emotions cannot be measured, but most of the emotions can be measured by means of GSR. First one is angry. It increases skin conductivity from a normal state, from a cool and composed state of a person. If the person is excited and reaches an angry state, then skin conductivity increases. The galvanic skin response decreases. It's inversely proportional, conductivity and resistivity. Next is fear bar disgust. For both fear and disgust, there is a decrease in skin conductivity. You can see here. So it will give a confusing output when the emotion is fear or disgust. Hence, it can be used either for fear or for disgust, or we can use different modalities to distinguish between these two. In the same way, for happiness, there is no change in skin conductivity, no change from the normal state. When a person goes to happiness, then there won't be any change. For surprise, there is an increase in skin conductivity, but the rate, even for anger, it is an increase. For surprise also it is increased. For sad also it is increased, but the amount by which it is increased varies. If we measure that amount, then we can distinguish whether it is a happy state or a surprise state or a sad state. This is about galvanic skin response, one of the important EDAs, electrodermal analysis, which is used in emotional affective computing. Second one is fingertip temperature. So fingertip temperature is another physiological parameter which is indicative of emotional status. So here, the change in temperature due to sweating is measured. Normally, the middle finger is used here for measuring the temperature. It increases for anger, decreases for fear, and unaltered for happy. So most of the times, by experience, by our experimentation, we have found out that fingertip temperature will not give us a major information about the emotional status, because the body temperature varies because of many reasons, because of various reasons, even due to the pathological condition of a person. If the person is in fever, then the temperature increases. right? And normally temperature measurement acts as a supplement to the GSR, galvanic skin response measurement. Okay, so on its own, normally people don't use fingertip temperature measurement as a parameter for detecting emotion. Third one is heart rate. So during changes in emotional state, heart rate also varies. If a person is calm and happy mood, heart rate remains in normal state. During the emotional conditions of angry, fear, surprise, and disgust, heart rate varies. Okay, so here also there is no much change between angry, fear, surprise, and disgust. There is a major change only in case of GSR. So using heart rate as a parameter increases the robustness of emotion detection system. If we go for multimodal at the sensor level, definitely robustness increases if we use more than one detection modality. Next is the features that we have used. First one is the segmentation of the facial components. First, segmentation of the mouth region, then segmentation of the eye region, various features of image processing of Python is used. The features of Python is used. Next, determination of facial attributes like mouth opening, eye opening, length of eyebrow constriction are all considered here. Like, so a histogram of the image is considered to detect how many white pixels are there in case of eye opening. Then area localization is done by means of template matching or by using a canny edge detector. All those can be implemented in Python. In the same way, biomedical parameters, GSR is measured by using a GSR meter. Then by FTT, temperature is measured by using any of the temperature sensing device. We have employed a thermistor because of very good sensitivity. That's what we need here. And heart rate is measured by means of photoplethysmography, which will give a better heart rate. I will show you the range of feature values. Are you able to see my word file? Can anyone of you turn off the mic and answer?
Yes, sir, it is okay.
Yes, sir, it's okay.
Okay. So range of the feature vector. So for the eye, it is the total number of white pixels in the eye. This value ranges from 179 to 490. Then the major axis and minor axis of the mouth opening, it ranges again from 179 to 490 in terms of number of pixels. Finally, using these values for training, we normalize that one. So then N max, it is the minor axis of the eye. Major axis won't change. Only the minor axis change during different emotional state. That indicates N max. L stands for length of the eyebrow constriction. It is from 12 to 18. It's a very small one. That angle, the change in the eyebrow constriction is considered here. So these are the 5 parameters. The first 5 are the feature vector corresponding to feature parameters corresponding to the facial expression. First one is number of white pixels in eye. Then major axis, if mouth is considered as an ellipse, then the minor axis, if mouth is an ellipse, then N max, minor axis of the eye, then the length of the eyebrow constriction. Next is the galvanic skin response. It ranges from 1 kilo ohm to 3.5 mega ohms. It is the resistance which will be converted in the GSR meter to the frequency of range 0 to 15 kilohertz. In the same way, fingertip temperature ranges 60 to 99 degree Fahrenheit. It is 15.5 to 37.2 degrees Celsius. This is what we can measure. Then heart rate, we use photoplethysmograph. The heart rate is higher in case of infants, but 10 years of age, the range of heart rate is 60 to 100. said, we have not used any infants in our experimentation. We use only adults. So this is the sample MCA database. So these parameters for different emotions. This is the normal, happy, surprise, sad, disgust, fear, and angry. Okay, so this is, I have shown this one for one subject. In the same way, we have created this one for many subjects by using experimenting. Let me go to the next slide. So far, we have only, acquired the data. Data don't make any sense. We will have to resort to statistics, not only statistics. We have to resort to the mathematics, the different tools of artificial intelligence, machine learning to detect what the emotion is. The next stage is that one. So since this FDP is on machine learning, artificial intelligence and machine learning, and already 2+ days of deliberations are over, you must be knowing about this MLP. MLP stands for multi-layer perceptron. One of the elementary and basic types of artificial neural networks. Okay, so I have considered this one. Even though we have worked and we are working on different other techniques, we are using SVM, we are using direction map, we are using genetical map algorithms, and in the algorithms we have tried with error back feed forward, error back propagation, then quasi-Newton, Levenberg-Marquardt. So in this session, I will stick myself only to MLP, and the most popular learning algorithm that is used in MLP is feed forward error back propagation algorithm. In our work also, we have considered only 3 layers. One input layer, a hidden layer, and an output layer. Right? So this is a typical multi-layer perceptron. The first one, these blue small circles indicate the input layer neurons, and these blue lines, which are connected to the hidden layer neurons. I have shown 2 hidden layer neurons here and 1 output layer neuron. Right? These blue colored arrows indicate the synaptic weight between the input layer and the hidden layer, also the hidden layer and the output layer. These are the synaptic weights. During the process of training, the synaptic weight changes. Thereby, the neural network will learn the input pattern. In the same way, the arrows specified in the red color, they indicate the bias. So here, bias at the hidden layer, bias at the output layer. Finally, this is the output of the classifier which indicates to which class the input belongs. After training, the same model can be used to apply the test input. Right? So this is a typical MLP. Next, I will explain a feed forward backpropagation algorithm, which you are familiar with. Probably it is a repetition, probably in the yesterday, day before yesterday, experts would have spoken about this one. In feed forward error backpropagation, there are 2 stages. First one is called forward propagation, and the second one is called backward propagation. During forward propagation, from the input layer to the hidden layer and to the output layer, the signal propagates. The signal propagates. Whereas in the back propagation, error is detected at the output, and that error will be propagated back, and during the period of back propagation, the synaptic weights of the neural network are updated. Okay, so let me go through each and every step one by one. In the first step, in the 0th step, the 0th step, since it is a supervised learning, You know what supervised learning is? A supervised learning is one where the expected pattern is given to the network. The expected output from the network is fed to the network. Then the network is trained so that the error is decreased, or the actual output of the network must be nearer to the expected output. So at the 0th step, you give the input, apply the input vector and the expected output. At step number 1, initialize weights and biases with random values. As I told, the synaptic weight and the biases to the neurons at the hidden layer and the output layer are first initialized to a random value. But after the first epoch, it will be altered, right? So take matrix dot product of input and weights, add biases. So this stage is called linear transformation. In case of linear transformation, the input is multiplied with the weight. It is called matrix dot product. The weight vector and input, the weight matrix and the input vector are multiplied. And to make the linear transformation, a fixed amount of value called bias, that bias will be added. The next stage is making it a non-linear transformation by using an activation function. So the output of the dot product along bias is applied through an activation function. There are different types of activation functions like sigmoid, hyperbolic tangent, linear, etc. In our work, we have used a sigmoid function. That is a third step. In the fourth step, perform a linear transformation on the hidden layer activation, then apply an activation function to predict the output. The second and third steps are for the neuron, and the fourth step is for the output layer neuron. Here also, taking the output from the hidden layer, get a dot product, that is linear transformation, the bias there also. Afterwards, again, use an activation function in the output layer also, so that it will produce an output. Then you compare that output with the expected output to get the error. That is the next stage. Okay, so in each stage, we can write mathematical equations. I have avoided mathematical equations here. Just have narrated the steps that are followed in the neural network. Next, in the backward propagation, so forward propagation goes from input layer to hidden layer to output layer. Whereas in back propagation, it starts from the output layer towards hidden layer, then to input layer. Right. So compare the prediction with actual output and calculate the gradient of error. Now, the actual output to the output layer is compared with the expected output. The result is the error. Then find the gradient of the error. How do you find the gradient of the error? By using first derivative. Do the first derivative of the error to give you the gradient. Then compute the slope and gradient of hidden and output layer neurons at both stages. Then compute the delta at the output layer, the small change that we have to do at the output. The synaptic weights which are connected in between the hidden layer and the output layer. This error will propagate back into the network. Take now the dot product of the output layer delta with the weight parameters. Then compute the delta hidden layer after computing the output layer. And step number 10, update weights at the output and hidden layer. Now, we change the weight because it's not learned properly. Hence, we have to change the synaptic weight so that we will learn. So update the biases at the output and hidden layer. So a small parameter called learning rate is used, which indicates the rate at which these values are to be updated. The synaptic weights, especially the synaptic weights and the biases. When we train second time, then updated bits and biases are used for forward propagation. So during this is the first epoch. An epoch consists of one forward and one backward propagation. After backward propagation, weights are now the same input is applied. In the forward propagation, again it goes from the input layer to output layer. Now the output is different because the dot product is different. Dot product is different because weights are different. Right. So one forward and one backward propagation iteration is considered as one training cycle. Right. So the neural network, as you know, will not learn in just one cycle or one epoch. It has to go for several cycles, then only it will learn. It may converge. There are instances it may diverge. Then we have to look into the entire architecture of the network. Coming to the implementation. So we have used, as I told, LabVIEW for the data acquisition purpose. Here the work is of twofold. One, do the data acquisition by using LabVIEW, capture the image, all the facial image, the expression are to be, to get the feature vector, we have to perform image processing operation. And for signals like GSR, FTT and HR, we have to do signal processing operation. Python is used here. As you know, the Python is a fantastic programming language. It's an interpreted language. I suggest the researchers who are searching for a new tool for their research work, go for Python. First one, it is open source, an advantage. A lot of groups are there which are working on various related domain of Python. And so the object-oriented programming can be easily implemented here. Whether it is a class, object, inheritance, polymorphism, you indicate, you say any of the features of object-oriented programming is there in C++ or Java can be easily implemented in Python. In addition to that one, Python has its own library, which is called modules, exclusively for biomedical engineering and biomedical image analysis. PyMIA, we call it as PyMIA, medical image analysis, PyMIC, medical image computing, this NeuroKit 2, which is used for biomedical signal processing, then NumPy, which is used for all numerical computations, then Matplotlib, which is used for plotting different types of graphs. Right? So Python is a very, very fantastic language. And in all our machine learning or pattern recognition applications, we have to use ordered sequences. Whether it's a vector or a matrix, ordered sequence. In Python, we have different ways of handling ordered sequences. There is a facility for string, there is a facility for tuple, a list, a dictionary, a range. These are the ordered sequences in Python, and methods are available to work on those ordered sequences. Right? So though there are so many programs that we have written, I will explain you only these 4 programs that I have shown here. Implementation by, first one is electrodermal analysis, EDA1, EDA2, which is basically used for galvanic skin response, and then PPG, photoplethysmography, which is used for heart rate measurement. Then finally, a simple back propagation neural network implementation where classification is done. Okay, so let me open my interpreter. The interpreter I am using is Anaconda with a spider. The distribution is Anaconda. Interpreter is the spider. Are you able to see my spider Python 3.7? Is my screen visible? One of you please unmute your mic and respond.
Yes, sir.
Yes, sir, visible.
Okay. So this is my first program, EDA1. So I have to import two modules as I already specified. First one is NeuroKit 2, which is used for biomedical signal processing. And second one is matplotlib, which is used for plotting. Okay, so then RC parameters, this is the figure. So I have to initialize a figure of this size 15.5. Don't worry much about it. Now this is my EDA signal. EDA simulate. I'm just simulating this one to show you here. During data acquisition, it will be directly taken by the lab view. Then it will be fed to my Python program. So its duration is 10, sampling rate is 250. SCR, this is cycles, skin response cycles. So I have indicated here as 3. That means I will get 3 cycles. If it is 4 cycles. So drift 0.01. So these are the parameters to be supplied for EDA simulate. Then that signal. Then we have another method called EDA process. So this will do pre-processing of the signals. So the applied input is EDA signal. You see here, which is the simulated signal at a sampling rate of 250. So finally, this is the signal, the clean signal after pre-processing and filtering. And these are some of the features: SCR onsets, SCR peaks, and SCR recovery. And finally, it is plotted. Now I run my program. Are you able to see this one? These are the waveforms corresponding to electrodermal activities. There are 3 SCRs here. You see here. This is the onset. Here it starts. The skin response. Initially, it is at the normal state. To a specific emotion, here it starts. It reaches the peak. Then it comes down. Here. Okay. So first one is called onset. And second one is the peak. And third one is the recovery. You see here. 3 points: red, blue, and orange of each cycle. So this is one cycle of GSR. Okay, so in the same way, I have one more program which is written for EDA. I will show that one, EDA2. Here, the parameters are also specified. You can see here, again, I have imported NeuroKit 2, matplotlib, then the parameters for plotting, then the first have simulated the signal, then processed the signal, then filtered to remove the noise. Now you have the features. First one is onset, second one is peaks, and third one is the recovery. And so it has been plotted now. Each signal is plotted. I will run this program and show you the output. You see here how it is different from the other one. So raw signal and clean signal. Okay, so and in our work, we use the peak value. It is not the onset value or the recovery value that is of importance to us. The peak value of GSR is very important, and we have considered that one in our work or as a feature vector. Next, let me go to the PPG. It's a very simple program. PPG stands for photoplethysmography. So photoplethysmography is one of the non-invasive techniques of measuring blood volume. Photoplethysmography is used for measuring blood volume, which can be related to heart rate. Okay, so it is normally, the photoplethysmograph is normally connected to the earlobes or to the fingertip, right? Then the change in the blood volume will be measured here, and that in turn will be converted into heart rate. A photo detector, a photocoupler is used here, a detector, a photo emitter, and a detector. And finally, the output is the amount of the light absorbed is measured. So here, as usual, the first line, import a neurokit, which is the module for biomedical signal processing, and you simulate PPG now. So simulate NK, this is my object. NK is the object of neurokit. Using the dot operator, you simulate PPG simulate. The duration is 15, sampling rate 250. So normal heart rate is 70. Then you then process the signal, you do pre-processing, then filtering the signal, taking the same sampling rate. Finally, you plot it. So now I clear the earlier one. And I execute this program. You see. So this is a photoplethysmogram, TPG, raw and clean signal. So the one which is in the background in blue color is the raw signal. And after pre-processing and filtering, the one which is shown here with the peak values is the photoplethysmography graph. And you can see here, the second graph will show the heart rate. Right? So this dotted line indicates the average value. This value changes for period of the period mentioned here. I have taken it for 15. The period here chosen is duration is 15 seconds, and the average value for 16 seconds is it's somewhere around 68. Somewhere around 68. So this type of a PPG signal that we will get, and this average value is taken as input for my analysis. Next, going to the last one, my back propagation algorithm. So whatever I have explained here in my back propagation algorithm, the same steps I am following, same one, initialize weights, biases, etc. I will show you the same thing here. First, import numpy. So it is a module used for numerical processing. Then this is my input array. Then just print input, print text. Then the y is my output 1 0 0. So though there are 3 outputs here, so I am interested only in the first one. The second and third are dummy. This is the actual output. The print y, you see here, print text statement first prints the input, then prints the output, defines sigmoid. You see here, the def keyword is used to define a function. Function is a subprogram. So we have a function for sigmoid. It returns 1 over 1 plus e to the power of minus x. That is the sigmoid activation function. So if we use hyperbolic tangent, it will be a bipolar sigmoid. I'm using a unipolar sigmoid. Next one is derivatives of sigmoid, which is used in back propagation for detecting the gradient. Right? So find the derivative x into 1 minus x. Next, initializing the variables. The total number of epochs I have considered here as 5000. LR stands for learning rate. As I told, it is the incremental value for the synoptic weight. It varies from 0 to 1. 1 at the highest, 0, there won't be any change in the learning rate. So I have taken a small value, it is 0.1. So input layer neurons, it corresponds to the shape of the input X. Then there are 3 hidden layer neurons and 1 output layer neurons. Then initialize weight and biases by using random uniform, by using the uniform distribution. The weights, WH stands for weights of the hidden layer neuron, BH biases of the hidden layer neurons, W out stands for the weights of the output layer neuron. In the same way, B out stands for bias of the output layer neurons that I have shown in my presentation slides. So by using the uniform distribution, the values are assigned. Okay, so the initial values, these are random in nature. When the epoch starts, these values will be altered. Now the training starts. So for I in range of epoch, 5,000, what's value we have given here? 5,000, yeah, 5,000. For I in range, a for loop. So this loop will be repeated from the for till BH. Remember, in Python, a function or a body of a loop is not enclosed inside flower brackets as in the case of C or C++. Here, an indentation. Indentation means a tab. A tab from the first column that itself indicates the body of the for loop or body of the function. You see here. So here, up to this point, it is at one tab. Then print is at the first column. So my for loop starts from here, goes up to this BH plus equals. Now you see here, these are the 6 statements written for forward propagation. For forward propagation, what we have to do? First one, get the dot product of the input and the weight. Then add the bias, BH, of the hidden layer. Then by using the sigmoid activation function, do the nonlinear transformation of the input, that is a hidden layer input, the same input. So then at the output layer, again perform the dot product matrix multiplication of the hidden layer activations with the weights which are connected in between the hidden layer neurons and the output layer neurons. Again, add the bias. Then finally, through the sigmoid, perform the nonlinear transformation. So these are the forward propagation from input layer up to hidden layer. Next, during back propagation, the very first step is to compute the error. So what is the error? It is the actual output that I have said at the beginning. This is Y, the expected output, minus the output produced by my network during forward propagation. Next, get the slope of one by using the first derivative of that one. So along with the sigmoid activation function, then multiply this error with the slope that has been computed. In the same sense, that is the error at the hidden layer. Also compute the error, the error at the output layer. Also compute the error. This is the error at the hidden layer, output layer and the hidden layer. So during this process, you see here, W out T. T stands for transformation, transpose, matrix transpose. W out dot T is the transpose of the weight matrix which are connected in between the hidden layer and the output layer. So this is needed because the number of columns of the first matrix must be equal to the number of rows in the second. Then only we can perform multiplication. We can perform dot product. So that is why the output vector, the output matrix, weight matrix has been transposed. You see here, there is no transpose during forward propagation, whereas during backward propagation, it is necessary for matching to perform the inner product. So we are transposing that matrix. So finally, weights are updated. W out, this is the weight vector in between the output and the hidden layer. Now we are coming backward. In the same way, WH, weight in between the hidden layer and the input layer. So it is outputted. Plus equals stands for add to the current value of W out. So it is the hidden layer activation function, which is the output multiplied by the slope, whole thing multiplied by the learning rate. The small increment 0.1, so which is the all values W out, B out, WH, BH, all are multiplied with the learning rate, and these are the new values W out, B out, WH, BH after the first epoch. And this loop will be repeated. The forward propagation, backward propagation, this for loop will be repeated how many times? 5,000 times. right? So it will be repeated 5,000 times. Then we feel that yes, my network has learned. Use the same network for doing testing and validation. Finally, so the print statement will print the output. What is the actual output of my system? It is not the Y. It is the output, actual output, whether my neural network has learned or not. Let me run this program. You can see here, this is my input. These are the actual output 100, but output of my trained network is 0.95071193, 0.04186340, 0.0044. You see here, the first value is nearer to 1, second and third value are nearer to 0. So network has learned to some extent. It's not an ideal network where the output is equal to Y, the expected output. If I run this program again, I may get different values. You see here, first is 0.95, then 0.041, the next one is 0.046, and the last one is 0.01, whereas it was 0.004. Right? After each training, so the values will change. Anyway, after the first set of 5,000 epochs, I am getting output which is nearer to the actual value. And in the second set also, I am getting the value which is nearer to the actual value. Then you retain this network and apply the new input, the one which has not been applied during training, but the data which has been acquired for all those parameters that we have chosen. So this is about the Python implementation. So coming to the database that we have created. So we have number of subjects or persons considered is equal to 180. The total number of records in our database is 180 into 7. Totally it is 1,260. So 180 persons, 7 means 6 emotions plus 1 neutral state. That's why totally 7 emotions. And total number of fields in one record is 5 plus 3 plus 1. So 5 facial parameters, 3 physiological parameters, and 1 output. 5 plus 3, they are for input, 1 output. So totally in our record, we have 9 fields. So age group of the subjects that we have selected, 20 to 55 years of age. So both male and female have been considered. I will just show you the field of, it's giving some problem. Let me open. Okay. Are you able to see my Word file?
Yes, sir. Visible, sir.
Field 1, field 2, field 3, field 4, field 5, up to field 9. Field 1, Mmax, Mmin, Nmax, eyebrow constriction, GSR, FTT, HR. These are all the input. So facial, first 5 facial action units, next 3 physiological parameters, the last one for emotion class. Okay, so in the output field, the class label is 1, 2, 3, 4, and 7. If it is 1, then it is a normal state or a neutral state. Then 2 for happy, 3 surprise, 4 sad, 5 disgust, then 6 fear, and 7 angry. Okay, so this is how our database looks like, and such 1,200 and something values are there in the database. So now we have almost come to the end of my presentation. After doing this work, the following conclusions can be drawn. We have taken 3 physiological parameters, GSR, FTT, heart rate, and 7 emotional status were considered. As already told, the result obtained clearly revealed that the galvanic skin response is the dominant feature compared to the remaining 2 physiological signals. I have not shown the table that I have, whatever the result that we have got, the correct recognition rate. Right. So after analyzing those values, the result that we have got, galvanic response, GSR, is playing a dominant role among all the features that So for the case of 2 and 3 physiological parameters, classifier exhibits a better recognition rates of 94.53 and 96.8. So if we considered 2 and 3 physiological parameters, so any two, GSR, FTT, or GSR, heart rate, etc., it gives a better recognition rate. If we consider more parameters, then the time taken for recognition will also increase. That is a drawback. The results obtained demonstrate the facial expression features with all 3 physiological parameters is the cream of the crop for input features. So that's what I am telling. If we consider all 5 plus 3 parameters, it is the best one. So what are the future avenues in this area? There's a lot of scope in this affective computing for researchers. The system can be made more robust by incorporating other dominant physiological parameters like EEG, face EMG, ERG, electroretinograph, the electrical activity of the eye, and blood flow, etc., into the feature vector. Then multimodal method of recognition of emotions can be realized by integrating features of speech signals like amplitude, pitch, etc. And feedback on the emotional status can be made available to the users of the computer system. This is really an application area. So whenever we are working on a system on a longer duration, if the system automatically recognizes it and plays a music which is soothing and which will activate our emotions, it will make us happy, joyful. So it is a sort of application. Maybe in the next generation computers that will be incorporated. The ANN can be expanded to identify the secondary emotions like tired, calm, bored, gloomy, etc. So here we have considered only the primary emotions. The secondary emotions can also be considered in the class. So as I told in the beginning, so I have a video. It's an initiative by Affective Computing Group at MIT Media Lab, Massachusetts. So they have devised a meter called mood meter, and it has been installed in the corridors of MIT. So let me play this one. It's a 3 or 4 minutes short video.
Have you ever wondered whether it's possible to quantitatively measure how friendly or welcoming a community is? Or imagined which parts of the community are happier than others? This project proposes a new technology that takes a stab at addressing these questions: the mood meter. The mood meter is an interactive technology that automatically encourages, recognizes, and counts the smiles of people in several locations. The information is captured and represented in a large-scale and time-changing emotional portrait. The overall system is based on a set of distributed installations that are strategically placed at locations with high pedestrian traffic. A camera constantly captures images of passers-by and sends them to a locally connected laptop. The laptop automatically analyzes each image and finds the number of faces and the intensity of their smiles. Our computer vision system utilizes OpenCV and Shore framework and extracts several geometric properties, such as the distances between the corner lips and the nose, that are used to predict intensity of a smile, ranging from 0% non-smiling to 100% very intense smiling. The information is shown to the passers-by in the form of a real-time interface. This interface shows a live feed of the camera and overlays a yellow neutral face if the person is not smiling, and a green happy smiley otherwise. On the left side of the interface display, there is a happiness barometer that shows the average smile intensity for everyone present in the image. Anonymous statistics from location, such as the number of faces and the average intensity of their smiles, are sent every 2 seconds to a website that aggregates and reflects the emotional landscape of the entire community. As part of the 150th anniversary of MIT, we proposed to use the mood meter to capture the emotional portrait of the campus during the festival. Over the 10 weeks of installation, thousands of people enjoyed interacting with the system in many different ways. Some students printed smiley faces and hung them on the wall in order to obtain the highest barometer readings on the campus. The overwhelming amount of positive feedback from the community regarding the study made us optimistic about future potential applications of Mood Meter. Technology and computer vision have reached a point where they can be deployed in the wild with certain reliability, but it is important to always be transparent and keep people informed. We look forward to a future when technologies use similar approaches to empower communities toward greater social awareness and discovery, and hopefully, these will elicit some smiles too.
Okay. So it has been clearly known that during the weekends or at the time of graduation day, students are very happy, but during the examination times, they are very, not that much happy. Anyway, maybe in the next generation mobile phones, we will get such features. Now only face detection mobile phones are available. In the next day, in the days to come, a mobile phone that detects different emotions so that we can improve our EQ. These are some of the important references that I have made. Some of the web links. I would like to show you some of the downloaded cartoons, which are which is significant now. Let us shut down all his body functions, then start them over again. That's the reason why computer engineers should not be surgeons. We electronics engineers, we are also like that. If a power function generator or power supply is not working, what we do, switch off first, then switch on. Most of the times it will work. If you want a second opinion, I will ask my computer. So that is the power of biomedical engineering. It's growing day by day. It is a pacemaker for your heart. Plus, you can download apps for your liver, kidneys, lungs, and pancreas. So technology of the future, maybe that is also available. And my final word. Are you concerned about the increase in artificial intelligence? No, but I am concerned about the decrease in real intelligence. You have seen the millennium students, those who born after 2000. So they have very good artificial intelligence, but unfortunately we have seen there is a decrease in real intelligence. And it is the responsibility of we teachers to increase their real intelligence also along with artificial intelligence. Both should go hand in hand so that it will be helpful to the mankind. Thank you very much for your patient listening. If you have any suggestions, feedback on improving my talk, most welcome. You can reach me please at gs@mchasan.ac.in. If you have any questions on this talk, I'm happy to answer. Thank you.
Hello, Shivkumar sir. Thank you very much, sir, for your valuable sharing of the research topic. A few other questions are already posted in the chat. Please, sir, you can go ahead.
So shall I ask one question, sir?
Sir, let the sir answer for the chat question, sir. You can post your questions to the chat.
Yes, yes, I am reading the questions. Yeah, there is one question. So thank you. If you have praised me, thank you very much. How to apply, this is from Golanapalli V. Prasad. How to apply AIML on written content to find the mood of a person? Oh, it's a good question. Oh, if for a mood, there are some set of words normally people use. So for happy, for joy, they use a set of words. By looking at those words, by means of text identification, we can definitely identify the mood. Next question is from Arpana Raval. The speaker has presented this topic with code illustrations, most effective one till date. Thanks a lot, sir. Thank you very much. Thank you very much. So nice session, Ranjit Kumar. Thank you.
Good afternoon, sir. This is Arpana Raval speaking to you. I had a question. Sir. Actually, I am into text analytics and natural language processing. So, like, I had also come across some projects regarding sentiment analysis and computing of the sentiment quotient. So, in this context, I would like to ask you the way you proceeded with your gesture computation and mood computation through speech signals. Should we proceed in a similar way so as to arrive at mood quotient on the basis of these sentiments, text sentiments?
Yeah, that is the actual way we have to go. In the same, even in text analysis, first you have to detect the features, then you choose a suitable classifier, then go on doing the analysis. And writing a code, in my experience, I am telling, writing a code is not a big issue. Choosing a problem and choosing a correct feature vector is very, very important.
Yes, sir. So because I was thinking the greatest utility of such kind of projects so as to compute the mood quotient and devising mood meter would be to combat the increasing levels of the depression that we have been observing in our youngster communities. So if we are able to design a very cheap model and a cost effective model, then we can really tell them that you evaluate yourselves minute after minute, day after day, week after week, such that they are out from this kind of low gestures and low moods, and they can keep their morals even in these harsh COVID times.
It is useful for counseling. It's very much essential for the younger generation. For counseling, definitely we can use this.
Sir, if you have come across certain papers regarding this utility with your you please share. I mean, I would like that if you share the papers.
Definitely, I will share whatever resources I have. Even I share whatever code that I have written with the organizers. Regarding the papers, you please send me a mail to gs@mcehostel.ac.
I have taken down your mail ID. I will send. Thank you, sir.
Yeah, thank you. Then Kanya Baswan, there's one more question. Are these techniques implemented in India? If yes, areas of implementation. Yes, it is at primitive stage in India. Few are working in this field. Especially one professor at University of Jadavpur called Amit Konar. He is working on this one. I have not seen any product as such. Most of these implementations are at academic level, at academic research.
Yes, sir. Absolute right, sir. Basically, sir, it's this portion totally is you can include the NLP, no? Natural language processing.
Yeah.
Human.
True.
Hello.
Yeah. Please.
Can we can use in this processing part in big data optimization technique?
No, I am new to that area. I am for optimization of big data optimization. I am not conversant with that one. I don't know. In fact, sorry.
Okay, sir.
Please send the recordings also. So thank you. It's from Deepthi Kulkarni. So I request organizers to send the recordings to me also.
Sir, can you please look into the chat box? I have posted my question. I'll be obliged if you answer that question to me, sir.
Which is your question, madam? So good database for EEG seizure detection.
Sir, can you please suggest the speech analysis? Can we do it through association rule based mining, sir, along with the NLP?
No, I am not into the speech signal processing. Probably today morning speaker, Professor Mahadev Prasanna,
Yes,
who
sir.
is an
Yes, sir.
authority in speech signal processing. I think I am not the right person to answer your question.
Thank you.
How to recognize negative and positive from Sushmita Das. Negative and positive emotion. If we can recognize an individual emotion, we can definitely recognize positive and negative emotion. Only the angry and sad are considered as negative emotion. All others are positive emotion. So after classification, if it belongs to those two, then it is negative, otherwise positive. Any more questions?
Hello. So this is Deepthi here again.
Yeah.
Yes,
Please,
sir.
please
I'm
go
very
ahead.
much new to this research, sir. I'm just completing my 6 months of research in PhD.
Yeah.
I am working on the similar scenario where I'm detecting emotions using EEG signals. So I just
Yeah.
wanted to ask, sir, like it is always in the beginning or the starting part, we need to find out the research gap, right? So research gap analysis, like after studying many of the papers. Exactly, sir. Can you suggest me how could I find out the research gap wherein like what exactly should be the research gap when we study all these papers related to the topic?
Okay. So to identify the research gap, you have to extensively review the literature. Extensively. By choosing a good impact factor journals. In the domain area in which, for example, you are using EEG analysis. In that area, in biomedical signal processing area, you do the extensive literature review. Most of the research that has been already carried out or people doing are normally published in such high impact factor journals. And you must be constantly in touch with your supervisor, because your supervisor has more experience and already carried out their research work. Okay, so actually there is no thumb rule how to identify the gap. But there are few areas where you can easily say no work has been done. I will give you an example. If you want to detect the water leakage in the underground pipeline without doing any earthwork, is it possible? Is such devices available? No. No such devices are available. A wireless type of device which will detect the exact location of the water leakage. I'm just citing an example. Such cases are also there in biomedical engineering. By means of extensive literature survey, you can identify the gap.
Thank you, sir. Thank you.
Thank you.
Sir, can you suggest good databases for EEG signals, sir?
For good database for EEG.
Yes, sir.
In the public domain,
signal detection.
Yeah. In the public domain, EEG signals, no, I have not seen. Even for GSR FTT, we don't have any databases. For EEG, it is not there. Those who are working in EEG field, they have a MOU or collaboration with hospitals. From the hospital, they are getting those EEG and they are creating their own, database. And here, clearance of ethical committee is also very much essential whenever you are working in the biomedical field. So in every district, there is an ethical committee. From the ethical committee, you have to get the clearance. So you have to create on your own. I have not seen any EEG database because of this reason. The patient's information should not be normally put into the public domain.
Okay, sir. Thank you, sir.
Hello, sir.
Yeah,
hello.
Please.
There is one more question from G. Prasad. How to take input of written content as input to analyze the presenter mode?
How to take input of written content as input to analyze the presenter mode. So during presentation, if a presenter writes something, I need a writing pad, I have to write something, then only you can identify the mode by means of written text analysis. Algorithms are available for written text analysis. I think he is specific about presenter mode. So when my Shivkumar is presenting, then listeners should know what is the mode of the presenter. Is it? Is question like that?
Yes, sir. Yes, sir. He has replied. Yes.
Yeah. Since I am not writing, you cannot identify the what are the words that I write.
Yes, sir. I think we are done with the queries, sir. Thank you so much, sir. Shivkumar sir, once again on behalf of the College of Engineering, Department of E&IE, and personally myself, I thank you once again.
Thank you all. Thank you UBDTC, and thank you all participants. Thank you very much.
Thank you, sir.